Separable differential equations. The purpose of this lesson is to introduce separable differential equations and go through the solutions of a few example problems. An equation such as this one, dy dx equals y sine x containing a derivative, is called a differential equation. To solve a differential equation, we must determine all the functions that satisfy the differential equation. An initial value problem requires determining a function y in terms of x when given its derivative and its output value for a particular input. The value of y for one particular value of x is the initial condition of the problem. There are 5 steps to solving a separable differential equation. Step 1 is to separate the variables. Step 2, find the antiderivative or integrate both sides of the equation. Step 3, plug in the numbers for the initial or given condition. Step 4, solve for the constant. And Step 5, plug the constant back into the equation integrated during Step 2 to get the particular equation. Now we have example 1. Find the particular equation that satisfies the initial condition, and the equation is dy dx equals x over y given as an initial condition of y of 0 equals 4. Step 1. Separate the variables. To separate the variable in this equation, we can cross multiply. After cross multiplying, here's the equation with the variables separated. We have y dy equals x dx. Now we go to step 2, integrate both sides of the equation. So we have the integral of y dy equals the integral of x dx. And that integration yields y squared over 2 equals x squared over 2 plus our constant of integration c. After multiplying both sides of the equation by 2, we get y squared equals x squared plus 2c. Now we'll let 2c equal c sub 2 to distinguish this constant as different from the original constant of integration c. Next, taking the square root of both sides of the equation to solve for y, we get y equals plus or minus the square root of quantity x squared plus c sub 2. Next, to evaluate which equation we use plus or minus, the result is positive because the output is 4 when x equals 0, so we can eliminate the negative option or equation. So we'll bring up to the top y equals the square root of quantity x squared plus c sub 2. Next we get to step 3, plug in the numbers for the initial condition, which will be 0 for x and 4 for y. Here's the equation with the numbers from the initial condition plugged in. We have 4 equals the square root of quantity 0 squared plus c sub 2. Now we get to step 4, solve for the constant. We'll solve for the constant by squaring both sides of the equation, and that squaring will give us 16 equals c sub 2. That brings us to step 5, substitute the constant into the equation. And plugging in the constant we found, 16 for c sub 2, we get y equals the square root of quantity x squared plus 16. And this is our particular equation, which we box in as our correct answer. Problem 2, solve y prime equals 3 sine x given y of 0 equals 2. Step 1, separate the variables. How are we going to do this? Where's the dy dx? Well, we can rewrite y prime as dy dx. Here's the differential equation rewritten as dy dx equals 3 sine x. Now we can cross multiply the dx, so we get dy equals 3 sine x dx. Now to step 2, integrate both sides of the equation. And here's the result of that integration. We have y equals negative 3 cosine x plus c. Now we get to step 3, plug in the numbers from the initial condition. So we'll plug in 2 for y and 0 for x. So this substitution gives us 2 equals negative 3 cosine of 0 plus c. Next we'll get to step 4, solve for the constant c. Well, the cosine of an angle of 0 is 1. So this gives us 2 equals negative 3 plus c. And solving for c, the constant c equals 5. And finally, step 5, use the constant to find the particular equation. And for that last step, we'll plug in 5 for c up here. So this gives us the particular equation y equals negative 3 cosine x plus 5. which we box in as our particular equation given our initial condition of y of 0 equals 2. Problem 3. Solve the differential equation dy dx equals 2xy minus 4x and find the solution that satisfies the initial condition y of 1 equals 3. Here's the equation from which we'll work on the left side. Again, we'll follow the steps. Step 1. Separate the variables. We see the x's and the y's mixed up on the right side, so we'll try to make order out of it. We'll do that by looking for the greatest common factor between these two terms, 2xy and negative 4x. And the greatest common factor to each term is 2x. So here's the equation rewritten with 2x factored out of each term on the right side. We have dy dx equals 2x times quantity y minus 2. And to separate the variables, we're going to cross multiply the dx and cross divide the y minus 2. And this is our result with the variables separated. We have dy over y minus 2 equals 2x dx. Now we get to step 2, integrate both sides of the equation. And here's the integral used on both sides of the equation. So we have the integral of dy over y minus 2 equals the integral of 2x dx. And now integrating both sides of the equation, we have the natural logarithm of the absolute value of quantity y minus 2 equals 2x squared over 2 plus c. On the right side of the equation, 2 over 2 cancel to equal 1. And now we'll bring up the natural logarithm of the absolute value of quantity y minus 2 equals x squared plus c, which we bring up to the top. Now having integrated, we get to step 3, plug in numbers from the initial condition. So plugging in 1 for x and 3 for y, we get the natural logarithm of quantity 3 minus 2 equals 1 squared plus the constant c. And that gives us the natural logarithm of 1 equals 1 plus c. Now we get to step 4, solve for the constant c. What is the natural logarithm of 1? Well, it's the answer to the question. What power do we have to raise the base e, or Euler's number 2, to equal 1? Well, e to the 0 power equals 1, so we have 0 equals 1 plus c. And solving for c, we have c equals negative 1. Now we go to step 5, plug c into the general solution and solve for y. So making that substitution, we have the natural logarithm of the absolute value of quantity y minus 2 equals x squared plus c. Raising both sides of the equation as powers of e, we get e to the power of the absolute value of quantity y minus 2 equals e to the power of quantity x squared minus 1. E to the power of natural logarithm cancel each other on the left side, so we have y minus 2 equals e to the power of quantity x squared minus 1. And solving for y, we get y equals e to the power of quantity x squared minus 1 plus 2, which we box in as our correct answer, our particular equation. Now we get to another type of situation illustrated by problem 4. Let y be a function of time. The rate of change dy dx is directly proportional to y. The proportion can be rewritten as dy dt equals ky. This is a particular category of differential equations. If y is a differential function of t such that y is greater than 0 and y prime equals ky for some constant k, the y equals c e to the power of kt, where c is the initial value of y and k is the proportionality constant. Exponential growth occurs where k is greater than 0 and exponential decay occurs where y is less than 0. Thus, this general formula along with its solution is a typecast for many applications showing exponential growth or decay. And as we have done before, we get to step 1, separate the variables. We can cross multiply the dt and cross divide the y. We now have the equation dy over y equals k dt. Now we'll get to step 2, integrate both sides of the equation. So we have the integral of dy over y equals the integral of k dt. And integrating, we get the natural logarithm of the absolute value of y equals kt plus c sub 1, c sub 1 being the constant of integration. In this example, we don't have an initial value that we can plug in for, but we'll go ahead and solve for y. And to solve for y, we'll rewrite both sides of the equation as exponents of Euler's number, or e. So we have e to the power of the logarithm of y equals e to the power of kt plus c sub 1. E to the power of the logarithm of base e cancel each other on the left side of the equation, so we're left with y equals e to the power of kt plus c sub 1, which we'll bring up to the top. Now all we have to do is simplify the right side of the equation. E to the power of kt plus c sub 1 can be rewritten as e to the power of kt times e to the power of c sub 1. Next, we can let e to the power of c sub 1 be a constant itself. And we'll call this newly created multiplying constant c, so we have y equals c times e to the power of kt. This equation is our general form of an exponential growth or decay equation. If k is greater than 1, we have growth. If k is less than 1, we have decline or decay. During this video lesson, we've solved 4 differential equation problems using this 5-step process, and we deliberately looked at problems that represented different looking varieties of these problems. I hope that this 5-step process can be a guidepost from which you can work as you start solving differential equations. This has been Solving Separable Differential Equations. Thanks for viewing.